Hello, everyone, and thank you for having me. Today, I'm going to talk about the RT Flow Template API, which is a new introduction to the RT Flow, basically. Okay, so some word about myself. My name is Ori Kam. I have over 20 years of experience in development. 6 out of them are in DPDK community, and I'm the RT Flow and regex maintainer. The outline for this presentation is basically a bit about the history of the RT Flow, what we learned when we worked in the RT Flow Template API, which was introduced last year, and some how-tos and tips to better utilize your application to use it and to better develop for it. In this graph, we basically see that in the x-axis, the years, while in the y-axis, we see the number of flows that the application requests to insert. As you can see, from 2015 to 2018, the application didn't request much flows. They were basically just control flows, match on ETH/tag, do RSS, and drop, that's it. Later on, application decided to request more actions, more items, number of flows increased. By 2021, we reached to around 1 million flows/rules per application. And by 2022, as we can see, a dramatic increase, which basically application wants to insert over 16 million rules. Actually, it wants to insert 16 million connections, not rules. And each connection it's at least bidirectional, so it means like 32 million rules, even more. So as we can see from relatively steady state with handful of rules, it was translated to many more rules, and in very, very short time, it was translated to millions of rules. So, how did it become so? So, like I said in the beginning, it was very simple rules, just control flows, match on Mac, match on VLAN tag, do RSS, do drop, that's it. Then, a request comes from the application, we want more flexibility. This was the time RT Flow was introduced. It was introduced when there were no rules and basically tried to give better control, better flexibility to add rules to the applications. And the rules were still designed to be controlled, but there were supposed to be many more rules and more flexible. So the idea was, and it quite was proven, that it will be easy to add new items. We cannot foresee which item the application will request. We cannot see which actions. So as long as the hardware can support it, we can expose it to the application. As we can see, it proved quite useful. So between 2018 to now, RT Flow action grew from around 10 to 50, and the items moved from about 20 to more than 70 different items that RT Flow constantly support. But during this time, basically, it was designed to be synchronous, it designed to be part of the control path. It was now designed to be multi-threaded. Again, the idea was the flexibility and to expose the hardware. By doing so, it basically opened the gate, and this gate basically allowed the application to offload rules, and they saw the light. So basically, by seeing the light, they wanted to insert much more rules, and much more than just control. And instead of controls, they moved to packet-driven or to data-driven rules. So a new era arrived, and basically, we needed something that scales up and gives the flexibility of the RTE flow, but also allows much faster insertion and support. So this is how we decided to implement the RT Template API, which is basically additional API introduced for the RT Flow. It was designed to be asynchronous by nature. It was designed as multi-threaded and almost no resource allocation. As previously stated in just the last presentation, malloc and everything is costly. Everything that should be done per rule, it's better to do it in advance. It will save time. Everything has a cost attached to it. So this is what the template API will try to solve. Sorry, it doesn't work. Am I missing something? Oh, Okay. So just to show the improvement. Basically, in this graph, on the x-axis, we can see the number of threads being used, while on the y-axis, we see the number of rules being inserted in kilos. So basically, if I'm looking at the one thread, the blue is the new template API, the red is the standard API. We see that in the template API, we managed to insert 1.3 million rules per second, while in the standard API, we are enabled to insert only 150K rules per second. A huge increasement in the template API. Additionally, what we can see is that between one thread and four thread, that the standard API moves from 151 to 160. We added 4 cores, we only got 10K or more rules to insert. While if we look at the template API, we can see that it scales much better, from 1.3 million to 2.4 million almost. A huge increase. I admit not linearly, there is limitation, but we still see a huge scalability. Basically, so we can see from this graph that the new template API is 10x faster than the standard one. One of the key aspects, like I mentioned before, is that the template API is configured except asynchronously and everything else, also to between control and data path. Everything we want to allocate is in the control path, so while you inserting the rules in the data path, there will be no allocation and nothing will be created new. So in this case, what we can see is that both of in the x-axis, we see the thread, in the y, the number of flows, the number of rules. Both of them, blue and red, are the template API. The only difference between those two is basically that we are saying, I want to insert 8 million rules, basically, with mark and RSS. We have 8 different RSS. But in the blue one, I'm configuring the RSS in the template. So it means every rule that uses this template will get the same RSS, and I'm simply creating 8 templates. While on the red, which uses the RSS, still 8, but I'm inserting the RSS when I'm inserting the rule. That's the only difference. We can see 21% improvement using the fixed action. Again, it's exactly the same. The only difference is if I declare in advance that I'm going to use specific RSS, or I'm letting the application, letting the PMD during rule insertion test if this RSS exists or not, or if it needs to be allocated or not. That's the only difference, and it's already increased our performance by 21%, which is, I think it's a huge number. At the end, offload, basically, the target of the application is never to offload rules. Offload rules is the means, it's not the end, it's not the objective. Applications is designed to do something with packets, process packets and do something with them. The idea of offloads is that if we can offload and we can save the application CPU time, allow it to do more, it's good. But as long as the application is basically doing partial offload, which means that it still answers the packets, it means that the application does 2 things. First of all, insert rules, and does the packet processing. So each CPU cycle that we take in order to insert rules means that it's less the CPU cycle that it has to process the packets. So in this table, I'm basically showing that the difference that the new template API almost takes no CPU cycles from the software. How do we see that? The first line, basically, we see a single rule. The single rule means that application just insert RSS and everything is handled in software. The second rule, the second line basically means application insert a rule per connection. The rule just marks the packet and does RSS. That's it. So basically, we are saving the application the ID of the packet. As you can see, the throughput is about the same. The CPU, with a small, neglectable throughput, and the CPU is the same. With this, sorry?
Speak on the microphone, please.
Sure. Yes. Sorry. Thanks. So basically, we can see that given the same CPU percentage, we managed to do the same throughput both without offload and offload. This means that the cost of offloading a rule, the application didn't notice it at all. This is a very big thing, because until now, there was all the questions, is it worth to offload the rule? Now we see that it doesn't cost. Just to make my point even more, to emphasize my point even more, is that you can see here the assumption, the comparison between the template API to the standard API. We have around 44K rules per second, and we see that the CPU cycle, I will start from the right, basically increases when we use the standard RT with about 4%, 3% actually. But more importantly, we see that the throughput drops from 48.5 to just 15. This means that the application, instead of processing those 48 gigabytes of bits, it was invested in offloading rules. This is not what we wanted. This is not the objective of rules. So basically, we can see that using the old API, not the old, standard API, basically the CPU and the application is involved in certain rules instead of doing what it should be doing, packet processing. Okay, so I hope that I showed until now that the API is good and it's nice and everybody should use it. But how do you use it best? How can you leverage your application? How can you leverage your code to use it? First of all, you need to understand that you need to learn your application. Just like any good developers here, I guess, and when you come to design a new feature, you're preparing, you're learning. So here you also need to learn about your application and probably need to modify it. You cannot take an application as is and use it, because you need to know what you can pre-allocate, what can be set as fixed, what must be kept as dynamic. So you need to learn the application and probably modify it. The second point is always use pre-allocated resources. Again, everything that you allocate during rule creation will cost you. Third point is interleave between hardware and software. The hardware works in parallel to the software, so you should avoid at all costs the thing that software works, and then hardware works, and then software works, and then hardware works. Basically, you're not utilizing the hardware. The hardware has the beautiful capability to work in total parallel to the software. So if the software works, also the hardware should work at the same given time. Last point that I want to make in this slide is basically every resource it counts, even the smallest, even what we think is neglectable, everything at the end is counted. We are talking about hardware, the hardware is limited. Limited resources, limited memory, cache misses. Everything that happens should be calculated for and justified. Everything here is nice, but how do you implement it? Let's look at that way. Let's see how can it be implemented. So in order to do that, let's take a simple test case, 5G VNF application. Basically, it's partially offloaded. For each connection, it needs to offload two rules, one RX, one TX. In the RX, we are matching 5 tuple, doing decap, mark action, and queue. For the TX, we are matching the 5 tuple and basically doing encap. The encap is per session and not per connection. Number of sessions in the system is 250K. Number of connections is 8 million. Each session is actually built of number of connection, so that's how we get it. Connection is a user basically, and like you know, every one of us here is basically much more utilizing. It's not just one connection that you're opening a lot more. Okay, so what can we do to improve? First of all, like I said, everything we should consider is pre-allocating. So as we saw from the RX, basically we have the decap, and then we have the mark and the queue. Decap is the same for all. Basically, we're just trimming the packet. It's not flow dependent. So let's do it fixed. Let's move it to the template API. Secondly, we have the mark. Mark can't be helped. It's per 5 tuple, must be kept as dynamic. Queue is interesting. It's per 5 tuple, but we have only like 8 queues. So we can use the RT flow handle and pre-create the action queue and simply reuse this action instead of, for each flow, insert queue action. So already we are basically moving from fixed, which is best, to a pre-allocated, the action handle, to the last one, which we cannot be avoided, which is dynamic per flow. like I said before, we need to interleave. So one way to do it is, for example, Rx burst and then running on all packets, and for each new connection that we want to offload, offload this connection. Insert TX rule, insert Rx rule, busy wait for completion. In this case, while we're inserting the rules, the hardware doesn't work. We want to achieve the interleaved. Basically, this can be achieved by using bulks. So basically, if I'm doing the same thing, Rx burst 256, I can say that I'm analyzing the packet only after 32 rules being inserted. I will push them really to the hardware, and then poll for completion. Again, not busy wait, just see if I get completion, and move to the next bulk. Basically, by working on the next bulk, the hardware works already on the previous bulk. So when the second bulk is complete, I will get every result from the hardware for the first bulk, and so on and so on. So basically, the hardware works in parallel. Every resource is valuable, and this is a bit tricky. Until now, it was relatively straightforward. Like we said in the TX, we want to NCAP. The NCAP is basically based on the sessions. We have only 250K sessions, while we have 8 million rules. What can we do to save this? So this means that we need 250 different NCAPs. So we can, in the naive way, create 8 millions and just reuse the NCAPs. But this means that we use the action, we pre-allocated everything, but we still inserted 8 million and we still wasted memory in order to hold all those rules. A better approach, a much better one, will be say, okay, I can, instead of match on 5 tuple, and since it's partially offloaded, the application can give me a metadata to say, okay, this flow belongs to some session. So basically, I don't need to match on 5 tuple, I need to match on a metadata supplied by the application, and just based on that, do the NCAP. This will result in that it will be very easy. There will be only 250K rules, each one with different NCAP, and we are simply matching those NCAPs. So much less resources are wasted. Okay, and a quick recap. The template API is much faster, it's 10x faster than the standard RTE flow. Keep that in mind. It's scalable, meaning we can use it in multi-cores. Unlike the standard API, which is blocks and everything, the idea of this API is to be used as between cores and multiple cores. It's data-oriented. We care about the data. Everything that is written in this API is data-sensitive. But it also means that in order to fully utilize it, you must understand your app and you must modify it. It doesn't work if the application doesn't match it. If, for example, you cannot know everything and you're doing everything for each flow, you will not get any benefit. The idea is what can be known and what, even if it's just part of them, it's good to have anything. And in any case, you need to think about maybe making changes to your application. The last thing basically is a call for action. You need to say, okay, first of all, from the driver manufacturers, add your driver. As long as one of the key points that makes the RT flow so widely used is everybody's contributing to it. So please contribute, add your PMD to it. Secondly, from application developers, add your application, make the changes, show example to other applications how it should be. For example, OVS is a use case. Everybody's learning and basically copying or duplicating the OVS and just making small changes. So if we do it right, everyone will copy the correct things and get a better performance. Questions?
Do we have any questions for Ori? Thank you.
Hi, so I've got one kind of complex question about the asynchronous nature. So there is a typical problem with this creating flows which are offloaded by hardware is by the time you receive the packet, you want to create a new rule, there are already dozens of packets waiting in a DMA queue. They should be, let's say, from the same rule. So once you send the rule to the hardware, it takes some delay. By the time it reaches the hardware, you've got another couple of dozen of packets which haven't been processed by the rule because the rule didn't get there, right? And now we need to figure out, okay, so I received the same packet, but I already sent the rule, so I need to keep some kind of a cache or whatever to memorize that you sent already the rule, or you just forget it and send the rule once again. The hardware has to figure out that you duplicated. So how do you solve this issue?
Very good questions. Very, very good questions. We encountered it, this scenario multiple times. Basically, it's depending on the application itself. Because, for example, there is application that says, okay, I prefer to insert the rule prior to the hardware because, for example, it's quota or it's meters. So it's important for me that the hardware will count everything. So I cannot skip. So basically, it means that I may re-inject the packet. I know this packet will be delayed in latency, but it will help me keep the hardware and be synchronized. And the quota will be correct, and the counters will be correct, and everything will be correct. So that's one way to re-inject the packet. Another way is, just like you said, keep it on the side until the flow is offloaded and only then pull, which will result in increased latency, but maybe that's the best solution for your application. And lastly, you can, if you don't care about hardware synchronization, you don't have quota, for example, and you care about latency, you can always say, okay, I'm doing everything also in software. I have the software pipe. Hopefully, the software pipe will be used only for a limited time set, but I can still, so it's very dependent on your application. Everything is supported, and like I said, you need to know your application to decide the best solution.
That use case you described, that's like a typical use case of an exception path, right? So part of the flows are processed in software, then they gradually become offloaded in hardware, but you need to like sync the state between those two. Okay, I get it. Thank you.
Yeah, connection tracking, for example, everything like this, that's a must. So that depends.
Okay, thank you.
Sure.
Do we have any other questions from Ori, either at home? You can put them in the chat or anyone physically here. Any thoughts, insights, etc.?
Thank you, guys.
Okay, thank you very much.
Thank you.
It was great. Really appreciate you coming down.